Hello, good afternoon. I'd like to continue with this design of flexible pavement. Previously, I've talked about the empirical approach. So I'll look at the example of the empirical approach, okay, for the design of the pavement. So in this case, we are going to talk further about the mechanistic procedure. So the structural model, the mechanistic procedure design process involves two stages. So first we need to establish the lots representing the traffic lots that apply to produce an instantaneous action. Okay, so we talk about the stress and strain. We need to establish what's the loading. So every rod there will be some traffic loading. So we need to find the design loading for the every pavement. So we need to get the design lots. Secondly, the effect of this action on the individual layers are examined to determine the ability to withstand repeated loads. Okay, so we need to usually there's a multi-layer approach. We need to find what happened to this traffic loading when they add on the various layers. It could be the wearing cost, so and then you have the best cost and sub best, and one of these could be cemented. Cement, that means that it's a bound layer cemented materials. So we need to see what are the responses, and also the subgrade as well. So there'll be various response to the traffic loading. For example, the cemented layers, it could crack under the repeated loading. So we have to consider that as well. And then some part, the wearing cost, it will crack after certain number of repeated loading, and the subgrade will be undergo this deformation, some sort of densification and then rutting. In the pavement model, each layer, including the subgrade, is considered to be comprised of homogeneous linear elastic material. So in this pavement model, we consider them as a homogeneous. Okay, so every part will be the same. That means that the x, y, z direction, they are the same materials. It is they're all the same in x, y, z direction, and there's linearly elastic material. That means that when you apply the loading, the traffic loading, when you remove the loading, it will bounce back to the z position. So this is the linear elastic model. So for the linear elastic model, there's A here, linear elastic, and then second one is non-linear elastic, and the third one is viscoelastic plastic. Okay, so our pavement model, we assume that it's a linear. So that means that is the perpendicular. So this one, the strain is proportional to the stress. Yes, proportionate. And then when you remove the stress, it will go back. It will bounce back with zero strain. Okay, so there's no, you go back to the zero strain. Yeah. Whereas for the non-elastic, it will not be proportionate. Rather, it will follow a curve. Okay, but it still bounce back. The elastic is still bounce back. But for the viscoelastic, so when you remove the stress, actually it will not bounce back to the original position. There will be some strain, there's some expansion, some deformations. So there's the length will be the dimension of the materials, pavement material. When you remove the loading, it will be sort of whether it's compressed or whether it's stretched. So there'll be some changes of the dimension, some deformation, or some in this case, rutting. In order to analyze the model, however, it's necessary that the material in each layer is characterized in terms of elastic stiffness property. So we need to characterize them as modulus and Poisson ratio. Probably not going too much about that. So this modulus is defined as the ratio of the stress along an axis over the ratio of strain. Okay, ratio of stress along that axis in the range of stress in which Hooke's law holds. So we look at the figure. It's linearly elastic, for the value stress over strain. So when you apply the load, the stress will proportional to the strain, and that means that when you apply loading, the expansion or the compression will be proportional to the stress. But when you remove it, it will go back along the same linear line and then back to zero. So there's no deformation. Poisson ratio is the fraction of expansion divided by the fraction of compression, or for small value of these changes. It's a fraction of percent of expansion divided by the fraction of compression, or small value. Okay, so yeah, so that's the definition. So I'm not going too much on these definitions. As pavement usually comprise a number of separate layers, layer elastic theory can be used to simplify the mathematics of solving the stress equations. So there are many layers. So we adopting this layer elastic theory. So some of the theory, the assumption is that the pavement layer extends indefinitely in the horizontal direction. The bottom layer, usually a subgrade, extends indefinitely downwards. Material are not stressed beyond the elastic range. Okay. So the input is that the modulus elasticity. So modulus and the Poisson ratio. So this one, the modulus MPa. Even so, the number of calculations needed to analyze even a simple pavement using any of these techniques is very large, and practical solution of them demands the use of a computer. So it's a tedious job. You want to do it manually. So even at the very early stages, of this one, the mechanistic approach, they make use of the computer to help to do the iterations. Humanly, I think it's a bit hard to do, is because talking about many iterations, 100 and 1,000 of them, so they need the use of the computer to do it. There are a number of software programs available for linear elastic model, but the program most commonly used in Australia is a Circle program. Circle. Okay, so I think we've been using the Circle 6, for the project 2. I think there are other programs as well in Asia and in North America and in Europe. So, but in Australia here, I think it's quite commonly used, Circle. In New Zealand, I think a lot of the consultants are using the Circle software as well. Material behavior. The damage produced by the material under repeated loading is dependent upon many factors, including the magnitude of the individual loads and the number of repetition of each load. So how much the damage produced by the size of the loading. How big is the tire, the wheel loading, the truck, the car wheel, the loading of the car will be quite small. One vehicle, motor vehicle, probably weigh about 1 ton. But for the truck, Easily it would be like 20 tons, one truck. And then if you got 10 1 2 3 4 5, if you got 6 wheel, sometimes you got 6 wheel, so each wheel will, you know, you 1 2 3 4 5, so you got 6 wheel. Yeah, that's right. You got the let's, for example, the 20 tons truck, you got 20 you got 6 wheel, so each wheel will be 3, at least it will exert like 3 tons on the ground. Whereas for the small car, the one, let's say 1.2 tons for 4 wheel, you have one wheel only exert about 300 kg. So it's quite a lot different. Like the big truck, you know, one, it can be the traffic loading for one wheel, it can be 10 times more than the small vehicle. So the magnitude of the individual load, performance of the material under the environmental condition. Okay, so the material which may vary during the life of pavement. So the performance of it is all different, you know, with temperature and age, you know, the for example, the wearing cost, when it's hot, it has is softer. When it's cold, it's harder. When the wearing cost is very old, it become very brittle. The performance not that is reduced. And also depend on the moisture. Some, let's say the wearing cost, not the wearing cost, but especially the subgrade. If it's very wet, then the performance is much reduced, because the carrying capacity is much reduced when the ground is wet. And to a certain extent, the pavement material as well, you know, is wet, probably the carrying capacity is going to reduce. Okay, just going to look at the repeated loading in screen capture video. There's a small clip. Just go.
Neglecting effect of fatigue factor. To understand what is fatigue, let's consider this metal wire. You have to break it. So how will you break it? Will you pull it from both ends, or will you do this, where you bend the wire upward and downward repetitively? Your answer is obviously the second option, because this method requires less effort compared to the first case. This is a well-known example of fatigue failure. So how does material fail due to fatigue? To get answer for this question, let us have a close look at stress variation in wire cross-section. When you bend it downwards, bending stress is induced in the wire. It will be tension at top area, and compression at bottom area. When wire is at equilibrium, there will not be any stress on wire cross-section. When wire is bending upwards, there will be compression at top and tension at bottom. So if you trace stress induced at a point with respect to time, it will vary like this. As a fluctuating stress with time. Initially the point will have positive stress. After that zero. Then negative stress. The same cycle repeats again and again. Such fluctuating stress is the root cause of fatigue failure. When such fluctuating stress act on a material, it will initiate something called micro crack. This crack will begin to grow with fluctuating load, and over time it will cause an abrupt failure. This is why failure due to fatigue is a dangerous affair. Unlike failure due to static load, fatigue failure happens without any warning, it doesn't even make a neck. And the failure is completely unpredictable.
Okay. So there's failure material, especially for the tensile loading. Okay, so you know, under the repetitive loading, so the pavement, the tensile, the layers undergoing the tensile stress, they will it could fail because of the repetitive loading and by fatigue, you know. The magnitude of the distress in most pavement materials has been found to be best explained by strand dependent relationship. Okay, the magnitude of the distress of most pavement material. So all the layers, the wearing cost, the wearing cost, and then the cemented layers, and the subgrade. Okay, so the for the pavement materials, if it's a granular layers, we don't consider the failure, because the failure, for the according to this elastic theory, all the failure, if it's a deformation, it only happens at the subgrade. So we only consider subgrade if there's deformation. So if there's any granular layer within the pavement, so we don't consider granular. That means that it's unbound, so we don't consider any failure. Okay, just I think it's understood that, you know, the thing, you know, the pavement, it just change. If the bottom sink, that it will just change shape. You know, it's not like not like the cemented material or the wearing cost. When they undergo the tension, there'll be some cracks, so there'll be some cracking. Also, there's a failure due to tensile tensile stress. In general, the allowable number of lots repetition is related to the inverse of the strength generated in the material by the passage of single lot repetition raised to an exponent. So we have this this expression. So n is the allowable number of lots repetition to failure. So this one is considered like each layers by layers for each layers. So each layers, the allowed number of repetition, maybe like how many repetition, 10 to the power of let's say 2 million repetition, something like that. So this one is based on this k divided by micro strength. So k is a fatigue constant, so it will be different for every type of material. It different from for wearing cost, for cemented material, for the subgrade. So b is a exponent b, and it's different for wearing cost, for the wearing surface cost, different for the cemented materials, for the subgrade. So for example, subgrade, the exponent is 7, the cemented material is 12, and the wearing cost is 7. And then this one, the micron strand, micro strand. So micro strand actually is a micro strand. So the strand that you measure, maybe you know, is quite small, but you you multiply by, because micro means 1,000, 1,000 micro. So everything, you know, is if you is for example, one divided by let's say it's actually for meter. Micrometer means that, you know, 10 to the power minus 6. 10 to the power minus 6. If it's mega, what's the other one? The other one is a kilometer. Kilometer is 10 to the power of 3. 10 to the power. So the other one is what's the other one? The 10 to the power 6. Okay, so this one, the strength. So what we do is that the strength, it could be quite small, like 10 to the power 6 or 10 to the power minus 5. It's quite small. So when we do, say, the micro strength, what we do is that we actually multiply by 1,000, so that not 1,000, 10 to the power 6 million. So we multiply, so it become a bigger figure. So I think the computer, they also do that. The computer, when they print out the result actually microstrand is actually the number, the strand already been multiplied by 1000. Okay, I think we'll look more about this expression later on. For this is general formula. Okay, for it we have a different sort of a different form. If it's for the like wearing for the surface cost, for the cemented materials, for the subgrade. Okay, so as I said earlier, the granular materials, if there's some unbound material layers within the pavement, we usually don't consider any failure for this unbound layers or the granular layers, because we said that deformations only happen at the subgrade. Okay, so we'll look more on this. We need to assign all the when design, we need to assign all the layers with the material properties, you know, that's for the for the surface cost, for the cemented layers, for the subgrade. The value of exponent varies with the type of pavement material. Values given by the Asphalt pavement design are summarized following. Asphalt is 5. Okay, yeah. So I think just now I mentioned 7. So actually it's a reverse. Subgrade is 7, asphalt is 5, and cemented material is 12. So this exponent here, the B. So this for this various type of material, the exponent asphalt is 5, cemented material is 12, subgrade is 7. Materials with higher exponent, primarily cemented materials, are very susceptible to damage by overloading because of fatigue relationship given in the equation below. So the one with high exponents is very prone to damage by overloading. So there'll be cracking, you know, the cemented material, there'll be cracking. But actually we can, even it's after cracking, they still have some usable resistance to the loading. So it's not considered as total failure. It just means it's just reduce sort of the allowance, the allowable loading. So even when the cemented material is cracked, so it doesn't mean that the pavement has failed already, but sort of it's reduced the allowable this one, the N. It still provide the resistance, you know, to the traffic loading, but sort of it has been reduced because of the crack. Okay, so we have when we do the pavement design, we have the option to consider whether the loading under the cracking, the cemented materials, whether you want to consider it with cracking or without cracking. So yeah, so this for the exponent. Pavement material can be classified into essentially 5 categories according to their fundamental behavior under the effect of applied loading. So there are these 5 materials: unbound granular materials, modified granular materials, cemented material, asphalt, concrete. Okay, we don't cover concrete because this one under the rigid pavement, so we cover the top 4. Other thing, I think the subgrade is under the category of unbound granular material as well. The soil, you know, is unbound granular materials. Unless you also you could sort of either you modify the subgrade, or you even could strengthen it, stabilize it. That means you stabilize it with cement or whatever. So you could do that as well for the subgrade. But that's you know, the material, the unbound granular materials, mostly is for the subgrade, and sometimes it's for part of the pavement material as well, part of the pavement layers. But the thing is that when it's unbound, we don't consider the damage. Okay, modify granular material and cemented material. Later we look at what's the difference between modified and cemented material. So then basically they have some sort of additives, but sort of this one is the modified material is less significant compared to the cemented material. Okay, asphalt is the surface cost. Okay, so we look at that later on. In the table 6.1 from Oxford Guide to the Pavement Technology Part 2, pavement structure design summarize the characteristics of various categories of pavement material. Specific comments related to each material category are included in the text. So the five materials. So the pavement 1, 2, 3, 4, 5. So it unbound granular material, modified granular material, cemented, asphalt. Okay, so we don't consider the concrete because this is under rigid. So you look at the material types. These are the the materials. Modify is the bitumen stabilized. Okay, so the unbound granular, it could be granular stabilized material. That means that this is the for example the ground, the subgrade. There could be some sort of granular stabilized. It could that means that is rather than cemented, it's a for example lime you could stabilize the material. You could stabilize the clay so that to provide the volumetric stabilization, so there's no change in volume. But sort of the lime doesn't really increase the strength of the clay. The one that increases strength actually is the cemented. The cement, you add cement to it, it will increase the strength. The lime normally doesn't increase the strength, mostly just to make it, to stabilize the clay. Okay. What does modify granular section? You could use a bitumen, you could use the chemically modified material. Cement, you can use cement, lime, fine ash, slag as well. Okay, cemented, all this. The difference is that the difference between modified and cemented is that there's no significant tensile strength. So there's no significant tensile strength. So that means that development shear strength through development of shear strength through particle interlock. So mostly is through the shear. That means that is the failure is deformations through shear and densification. So actually, compared to this, we have the cemented material. So development of shear strength through particles interlock and chemical bonding, so significant tensile strength. So that's cracking developed through shrinkage, fatigue, and overstressing, erosion, pumping. So when you consider, actually, this one, the modified material and the cemented material, actually, we just we have to input the modulus and Poisson ratio. Actually, I did mention that the deformation, it will not happen in the pavement layers above the subgrade. The deformation we assume that in the elastic theory is only happen at the subgrade. Okay, deformation. So in a way, the modified granular material, the layers, if there is no significant tensile strength, we assume that it will not fail by there's no deformations. Okay, even though there might be some sort of shift, the things might sink, densification, but the deformation is only happen, we assume it to be happen as subgrade rather than the layers above. So we don't consider any like tensile failure for the modified granular section. Okay, even though we add something, there might be some cement, so only for we consider tensile crack only for the cemented section, not the modified section. Asphalt the same as a cemented layer, they exhibit significant tensile strength. Okay, so there'll be some tensile cracking. We consider the tensile, this one the failure due to tensile strength. Okay, so we consider the tensile cracks for both the cemented and the cemented section as well as the asphalt. Whereas this one we don't, modify layer we don't, but it can improve the strength because it has a higher modulus. So the strength, it has contributing factor, so it could contribute the overall strength. It can compare, if it's modified or unmodified, that means that it is unbound. So actually this one has if you add something additives, it will significantly increase the strength, so it contribute to the layer thickness. It could probably, if you modify, it could have a thinner layers in some contributions. Mechanistic method of design of flexible pavement requires the material to be characterized in terms of the elastic properties. So we need to input the modulus and Poisson ratio. Subgrade. The vertical modulus of subgrade can be determined from laboratory testing of conditional specimen or by using empirical relationship. So we modulus, we said that is 10 times CBR. Okay, the equation is at best an approximation, and modulus has been found to vary in the range of 5 times CBR to 20 times CBR. Okay, a maximum value of 150 MPa is normally adopted for subgrade materials. So the average could be, normally we compact the subgrade to about 10 CBR. 10 CBR, the subgrade. So normally it's like below 10 and not above 10. You could, like starting from, let's say 3 until 10, the subgrade you can compare. So so let's say 10 times 10 will be about CBR 10 will be 100. So here maximum value of 150. So because the CBR here is between, actually in the range between 5 and 20. So the maximum shouldn't go beyond 150. Normally, the CBR, you compare it to let's say compared to 8. CBR go 8 for the best, for the subgrade. So 8 times 10 will be 80 only. So based on your design, you could compact your subgrade, let's say from 3 to 10%. You just multiply by 10. Okay. Representative values of Poisson ratios for subgrade are 0.45 for cohesive material and 0.35 for the non-cohesive material. The limiting strength criterion for the subgrade is given by the following equation. So this is the limiting strength criterion, is the allowable. N is allowable number of repetition of a standard axle at this strength before an unacceptable level of permanent deformation develop. That means that if the allowable is so much, your design loading, your traffic loading, you exceed that, then exceed the allowable, then the in this case the subgrade is going to fail. Okay, so in this case, N is equal to the K here. You know, previously we have a K. K here. For the subgrade is 9,300, and this thing the microstrand. So we don't know microstrand. We have to do the iterations. We use the computer. You know, we just actually this one is we do try and error. We try the certain design, the design based on design loading, and then through the iteration it can give us how much is the microstrand. Okay, microstrand. So and this one, the design loading should not be greater than the allowable number of repetitions. Okay, this one is based on actually from the so this one is, you know, this is from the formula, from the iterations. We will get that from the iteration. So we can develop an allowable number of repetition for the material. So you, after you run the program, because you can get this from the program, for the circuit program, you run the iteration. So we could have a, you know, design traffic of for example certain value, let's say 70 million ESA. Or later on we said that is we call we have to convert to the standard Excel repetitions. Okay, we will look at that. There need to be the units for allowable should be the same as for the design loading. You know, the design the traffic loading. So but because the response of the different layers are different, you know, for the asphalt or the wearing the surface course is different from the response of the cemented layers, and it's different from the response of the subgrade. So we have a different allowable number of repetition of standard Excel. Actually, later on we see that this one, the repetition is SAR. SAR stands for standard Excel repetitions. So they have all different, even though the design loading is the same. The design loading ESA design, so the traffic loading is ESA, equivalent standard Excel, maybe about, let's say, 70 million within a span, you know, the design period, let's say about 15 years. So the design traffic is let's say 70 million ESA. Then you have to this 70 million ESA, you have to change to the for the asphalt. What is it equivalent to the standard Excel SAR for the varying cost? What is it equivalent to the SAR equivalent to the cemented layer? What's it equivalent to the subgrade in SAR for the, you know? Then you can compare the design traffic and the allowable, see whether, you know, is it when we design, that means that whatever the design value must be below the allowable, so to prevent any failure. Yeah. So for the subgrade, this is the expression for the allowable number of repetitions that will prevent the subgrade to fail. For the cemented layers, we got quite a lot of things, you know, all the materials, best quality, all these things. Okay, so these are all the material properties which you can use. You want to use whichever, you know, the type of the range of modulus, 5,000 to 15,000, 3,000 to 8,000, 2,000 to 5,000, 1,500 to 3,000. Different type of, because your cemented material, it could be at the best, it could be at the sub best. So even the link grade concrete, this one's probably for the I think rigid, for the rigid pavement. Okay, so this one you can choose the range of the modulus from different type. of material for either is for the best or for the sub best. Okay, so and for the Poisson ratio, there are some range you can choose as well. So typically, the criterion for the cemented material is this is the expression, the K. You know, the previously we have K here. The K here is now in this expression. The whole thing is K. The micron, this is the microstrand, and then we in front we put a RF, and here the exponent is 12, which is the the one for the cemented material. The exponent is 12. So this one, the N is allowable number of repetitions. Microstrand is the tensile strength produced by the load. E is the cemented material modulus. RF is the reliability factor for cemented material fatigue. So you want to design the reliability. If you want to have higher reliability, then the allowable loading, you need to reduce it. If you want to more reliable, then the allowable loading should be decreased. If you want to have less reliability, so you could increase the allowable loading. So that means that you not so for example, allowable loading, let's say for example is 100%. Okay, let's say the very high, maybe let's say you want the very reliable, you need to lower down the allowable repetition, for example, to 2 million repetition. So if the design traffic reach 2 million, it will fail. But if you want to be less reliable, you could increase the allowable to like 3 million or 4 million. Okay, so that's so this is a factor here, that 3 times, 0.5 times, 1 time, 2 times. So for example here, if you want to have here we didn't have the 100%. 100% is, for example, we have 2 million. Let's say the repetitive, the standard axle repetitions for the allowable 2 million. Okay, for let's say that means if you have 80%, you have to increase the load by 4.7 times. So will be about 8 or 9 million repetitions. So that means that you can increase the allowable loading, but it's less reliable. So even when it be more reliable, that means that it has to hit the bottom one first. If you got the value is lower, then it's more reliable. It's less prone. If your value is very high, it could fail anytime. So it's less reliable. Asphalt. So the asphalt they can use, you have depending on the size of particles, 10, 14 or 20 in the range, you could use class 70, 170, class 320, class 600 multigrade, or this one is I think is the what's it called, the emotion. Okay, so and these are these are equivalent to these are the Australian binder compared to the New Zealand. These are the equivalent to New Zealand binder. So you could choose any type of the mixed type, the modulus. Okay, so any type of this based on your design. And the fatigue criteria for asphalt is the K. The top one is a K. The whole thing is K, and actually no, this K actually is 6918 into at 0.856 VP plus 1.08, whole thing divided by S mix to a power of 0.36, and then this is a microstrand here, and for the exponent here for the asphalt, which is 5. Just now we said the cemented material is 12, subgrade is 7. So VP is percentage of volume of bitumen in the asphalt. How much? S mix is a asphalt modulus. RF reliability factor for asphalt. Asphalt thickness. So if you want to be less reliable, then you the value become bigger. So your allowable become bigger. If you want to be more reliable, then your number is smaller. So the number, the n will be smaller. So this is the expression for the asphalt. So the mechanistic procedure, you just input the asphalt, you know, the thickness. You have to input the thickness. You try the thickness. You just choose the thickness, and then the subgrade modulus, you can choose the thickness in the subgrade modulus. So because of trial pavement, you have to input the thickness for the asphalt, and then what's the property, what's the strength, you have to input what's the modulus, what is the Poisson ratio for the asphalt, and then you have to input the what is that? Modulus for the this one, the okay, actually there's some chart here, you know, the chart, the example charts. These are the mechanisms, the example chart. You have to input the I think the cemented material as well, the cemented materials, and you have different type of, you have to input the thickness of the cemented layers and also the material properties. Okay, and we use all this expression to come up with the allowable standard axial repetitions for the, you know, this one for asphalt, for the cemented materials, for the permanent deformation actually is applied to the subgrade. Okay, there are 15 design charts for mechanistic design in Asphalt, but only a few are shown. This chart, we cannot use this chart for thickness design. You know, the chart for thickness design only for the empirical approach. This one we don't. These charts are not for. There are some of these charts. You know, I only put a few charts: ECO1, ECO3, ECO5, ECO9, ECO10. So these are few charts. Actually, they got more charts. But these charts, they serve as an illustration of the application of mechanistic design procedure for flexible pavement and may be useful in selecting a trial pavement configuration. It's only useful for select a trial pavement configuration. It's not for design. You have a trial pavement, and then you put in all the trial pavement. That means that you put in the thickness of the different layers for the asphalt, for the cemented material, for the subgrade. There's no thickness. You put in the material properties. You put in the, you know, what's that? The modulus, the Poisson ratio for each of the layers, and then run the software. Okay. Then you, from the when you run the software, you know, you can obtain actually the micro strength, and then so these are the charts that we see. You know, this one is not for design, but for actually can be used for the to do the trial pavement. You cannot base on this to design the thickness of the pavement based by the mechanistic approach. This is not the way. This is just for demonstration. So you could try the different granular material, because this one only the granular material. You could so you have a, let's say you just have a granular material against the thickness of asphalt. So you choose, for example, your granular material is maybe 200, thickness 200, and then your asphalt is 200. You know, roughly, you know, it could be able to withstand a traffic. This is the what's that? Design loading. This is ESA. 200 tick and then 200 tick of the unbound material. It could withstand about 2 times 10 to the power 6 ESA. This is based on the asphalt. This type of modulus, this type of asphalt, 300 MPa, and the subgrade subgrade is about 30 MPa. So 30 maybe about 3%, because the subgrade is like 10 times CBR. So CBR is about 3%. So if this one is asphalt is 300, the subgrade is changed to 70 MPa. It's about 7 CBR equals 7. So the thing is different, and this another design. You have the subgrade modulus, and then you have the thickness of asphalt, and then you have design traffic. They got different form, thickness, and then cemented material. So you can compare cement. If you have cemented materials, and then the asphalt, and then what you have, let's say your subgrade is 50 MPa. Actually it's about 5%. So cemented material, this is amount is 2000 MPa, asphalt is 3000. So roughly you can get, if you have this type of thickness, of cemented material, this is the thickness of the asphalt. You can see whether it is able to withstand the traffic that you want to. Maybe your traffic you want to is maybe, this is 2 times 10 to the power 7, somewhere there, between 10 to the power 7 and 10 to the power 8. Okay, so it's good for the trial pavement to find the trial thickness. Effect of asphalt thickness of on factored life of asphalt surface pavement. So for a given design traffic, asphalt thickness, asphalt stiffness. For a given design traffic, asphalt stiffness, thickness of granular or cemented base or sub-base, and subgrade stiffness. Two thickness of asphalt provide the same theoretical fatigue performance. So for the different material property, for the same, for the let's say there's one trial pavement, you have a given design traffic, you have the asphalt thickness, stiffness, the thickness, and then you got the granular or cemented base or sub-base and subgrade thickness, stiffness. But two type of thickness can provide the same theoretical fatigue performance. An example of this is in chart ECO1, where effective life of 2 times 10 to the power, this one should be 10 to the power 5 ESA, not 105. 2 times 10 to the power 5 ECA can be obtained by using either 40 mm or 70 mm asphalt on a 440 mm granular material. Okay, so look at this. This one is the for this curve, this particular curve, 2 times 10 to the power 5 ESA. You see this curve here, 2 times 10 to the power 5 ESA. And for this particular, the asphalt is 3000 MPa. About subgrade is 30 MPa, it's about 3%. So because this curve is like this, so actually the thickness of unbound granular material is 440. This is here, but it cut this line, the red line here, cut the curve twice. First time it cut at 40 mm, and then secondly it cut at about 70. So that's why it says that the same performance, same, it can have a the fatted life of 2 times 10 to the 5. So you can achieve that. So that means that you have granular material is 440 thick, and then either you got 70 thickness of asphalt, or 40 or 70, it can produce the same fatigue, the design traffic of 2 times 10 to the power 5. Either the pavement, the asphalt, either is thickness asphalt, either it's 40 or 70, it can produce the same 2 times 10 to the power 5 ESA. So as the asphalt thickness is increased, the horizontal strand increase from the negative value to low positive value. So asphalt thickness increase, horizontal strand increase from negative value to a low. So look at that. So when the asphalt thickness increase here, the initially is strand, that is very asphalt is maybe very, let's say 50 mm. Let's say, here actually the peak is 40, and let's say 20 mm. So initially it's compression, because for example, if it's what's that, the spray seal or chip seal, is mostly under compression. All the things will be under compression. The granular material will be under compression. There's no tension. So if it's very thin, it's mostly under compression. But when it's become thicker, it will separate out. The bottom become compression tension, the top become, because it's bent, the bottom become tension, the top part become compression. So so it will the strand at the base of the asphalt, strand at the base of asphalt, that means at the bottom. So before that it was compression, and then slowly when the thickness increase, most of them become tensile, the bottom. So you're going to this curve, the tensile strength will increase, the thickness increase, but at certain thickness, more than certain thickness, the tensile strength will reach the top, it will reach the maximum, and then it will decrease again when the asphalt become very thick, So this figure general relationship between asphalt thickness and horizontal strand at the base of the asphalt layers. Asphalt layers, which are relatively thin, offer little resistance to the fracture of the underlying structure. In this range of thickness, the greater the depth of the asphalt, the greater the magnitude of the tensile strength induced at its underside. So in this range, very thin, when you increase the thickness from here to before the peak, so the greater the thickness, the strength, the greater the magnitude of tensile strength induced at its underside. So for this one, before this peak, when you increase the thickness, the tensile strength will increase at the bottom. Okay, only after you pass the peak, then actually when you increase the thickness, the tensile strength, the strength of the base of the asphalt, the tensile strength will decrease with thickness. So a peak strength level is reached usually in the range of 40 to 80 mm for highway traffic loading. Further increase in asphalt thickness reduce the flexure of the structure and resulting strength. So actually, this 40 to 80, it has a maximum, the biggest tensile strength. So it's not very desirable. Actually, we should go for bigger, so that you don't have that high tensile strength. Because if high tensile strength, you have a more chances of failure. You will reach the failure earlier. Okay, so but if you have a lower, thicker, okay, if it's thicker, then it's better. Where is here, is too thin, then it has no structural. It doesn't. You could have it has a low tension, mostly it's compression, just like for spray, the chip seal, but it doesn't contribute to any strength any strand of the pavement. Only when it's thicker, you know, the pavement is thicker, the asphalt is thicker, it contribute to the strand of the pavement. All cemented treated beds will crack, initially due to shrinkage cracking following construction, and later in the life of the pavement when fatigue cracking from the cemented layer will occur. A minimum thickness of conventional dense graded asphalt is of 175 mm is generally recommended to retard surface cracking. So we don't want to have the cracking, you know. If you got maximum cracking, the range of maximum cracking, that means that between 40 to 80 mm asphalt, then the chances of cracking is very big. When the bottom crack, it will reflect to the top. You can so the top will crack as well. So, but if you got 175, so actually the 175 probably somewhere here. So the tensile strength, the tensile stress probably is less at that point. So you so when you use the thicker asphalt, it will retard the surface cracking. So the chances of cracking is less because the tensile strength is lower at the higher thickness. The other thing that we can do is that the use of strand elevating membrane I think we studied before in the highway 1, strand elevating membrane interlayer, or the use of modified binder can enable acceptable pavement life to be achieved with a much reduced thickness of asphalt. So you could do, if you want to reduce the the asphalt thickness, you could implement this you know, the same. So that one you know it will, or the other you use other type of modified binder. If your binder is a PMB, the polymer modified binder, so actually you change the graph, you know, you change the graph. So the tensile strength, it could be very high, the tensile strength, but because the binder is strong, so actually it is able to sustain it. It can have more highest tensile resistance. So even though it reached a peak, it can prevent it from cracking. Okay, so that can be achieved by the higher quality binder, or you put this semi below the pavement. You can below the asphalt. You can achieve that. Another option is to deal with the cracking is to incorporate a cement treated sub base, which has 100 mm thick unbound granular base. They are placed between the asphalt and the cemented treated sub base. So that means that above the subgrade, you have the cement treated sub. This one is called sub base anyway. This is a cement treated sub base. You have a cement treated sub base, but it's not directly in contact with the asphalt. But there's a unbound granular material, just aggregates 100 mm thick. You place it between the CTSB and the asphalt. Actually, this one you can retard the cracking as well. This one, because this CTSB can crack, but because there's 100 mm thick, this one, the unbound aggregate, is a buffer, so the crack will be sort of contained. It will not reach that, you know. If you this CTSB is directly below the asphalt, then any crack here, it will reflect. You can sort of the crack can propagate to the top, you know, asphalt. But you put this buffer material, you know, the in between this 100 mm of unbound granular material. Actually, the crack will be contained. It will not reach to the asphalt. So the mechanistic procedure from these are the we use this one, the crack. I think we talked about before. So these are the based on this, you know, the 1, 2, 3 one is the tensile crack at the bottom of asphalt. 2 is the tensile strength at the bottom of cemented material. It's cemented material. So granular material, we don't do any. There's no failure. We don't consider any failure. And for the 3 is compressive strength at top of subgrade. That's top subgrade. There's some compressive failure. Yeah. So actually, these are the steps of the for mechanistic approach. These are the input requirements. What are the things that you need to input? Also, you design the number of ESA as well. This one you have to be compute separately. Determine the design number of ESA. There's another formula under the design traffic to do that. So all the material properties you need to input. You know, what are the modulus, what are the Poisson ratio, and then you have to input the thickness of each layers as well. And then you have this one, the calculation of critical strength. You have to do the calculations. This one mostly done by the these are the the manual step, but actually we do it by the Circuit software. The Circuit software will take care of all these things. You have to input all these things, input all the parameters for the input parameters, and then you just enter it. You go into the Circuit software. It will come out with answer. Okay, I think so. I'm not going to talk too much about that. So the next topic will be the design traffic. I will talk about later on. So I think we'll stop here for the mechanistic approach. Okay.